Yeah. Hello. I'm closing my phone.
Sir, your mic is on.
Yeah, yeah.
And you can.
Video is on.
No, video is off. You can.
No. Video. No.
No, video is still off. I think.
Hello.
I think there's a lag, sir.
Stop sharing.
Yes, sir.
It's a long time to start again. Yeah, then what is the problem? I can hear you all.
I think there's a
Can I
lag.
start? You start first and then I carry on.
Yes, sir. So we can begin.
Oh,
Alvin, you can start.
Hello everyone.
start and let me know when you can hear me or see me or not.
So pleasant evening to everyone.
The thing is, I can't cut off my video. Hello. Hello. Yeah.
Sir, you can continue. You are audible.
See now. Yeah. Yeah, so I'm cutting off the video. What? Okay?
Yes, sir.
My video just now is off. You carry on.
Yeah. Yeah, we can begin
You
again.
carry on.
Hello everyone and a pleasant evening. A warm welcome to everyone to this introductory session for our annual magazine Celeritas 2021. This is the day that we have all been waiting for quite some time, and the Sigma Phi team has put in tremendous work to bring Celeritas to life. Today's session will witness the unveiling of the cover of Celeritas and a brief overview of the magazine by the editorial team members. For this occasion, we have invited amongst us our chief guest, a very celebrated person from the Xavier's family, associated with us from time immemorial, Dr. Jehangir Mistry. Before we dive into the session, I call upon the chairperson of the Society of Physics, Sigma Phi, Emma Jane Choker, to familiarize the audience with the society. The stage is yours, Emma.
Okay, I think Emma's not been able to join the meeting because of some network issues. So I'll be introducing. Basically, we are the Society of Physics, popularly known as Sigma Phi, and we were founded in 2017. And we are a bunch of young physics enthusiasts, all college students of Xavier's, who basically strive to achieve like how to popularize science to spread the joy of physics that we all feel while studying physics. And these are like just one of our events where we show you how academics can be much more interesting. It can be much more fun. So without saying more, I'm very excited for this event. So I hope you guys are too. I think we can proceed.
Yeah, indeed, physics is a subject that connects us to nature and provides a deeper insight to the world around us. Truly a beautiful feat. Thank you, Akshita. Coming to the main part of the evening, we have a person with a very popular name on the college campus, owing to his long-lasting affiliation to the institution. Dr. Jehangir Mistry has been associated with St. Xavier's College during the three prime phases of his life. He completed his schooling from St. Xavier's High School, Fort, and then joined St. Xavier's College for his undergraduate degree in physics. He then went on for a master's, followed by a doctorate in physics in the field of laser spectroscopy from the prestigious Baba Atomic Research Center in Chembur. Soon after, he returned back to St. Xavier's as a lecturer in the Department of Physics. He was elevated to the post of Vice Principal of Academic Improvement in 1985. And the teacher assessment questionnaire, that is the form that we fill before the end semesters to get our hall tickets, it was upgraded and continued by Dr. Mistry during his tenure. An avid science communicator, he's a member of various associations, and just to name a very handful of the many of them, the Indian Association of Physics Teachers, the Astronomical Society of India, and him being the founding member of the Amateur Astronomers Association. Outside Xavier's, Dr. Mistry has given and conducted many sessions on teacher training in educational institutions and acted as as a judge for events. He retired as a physics professor after 38 years of service, but once again, he returned back as the director of Xavier Institute of Communication, the building that we see, or rather unfortunately used to see during our time in the woods. In XIC, Xavier Institute of Communication, Dr. Mistry started with video editing and graphic designing, having begun the first computer graphics training in India at that time. His current task involves selection of students at XIC and designing its syllabus. Apart from cinematography and computer graphics, Dr. Mistry is extremely passionate about photography. After that introduction about Dr. Mistry, let us listen to him himself about his journey as a student and professor and other discussions about physics. To the audience, feel free to ask questions in the chat during the talk and unmute and engage in a conversation after the talk. Dr. Mistry encourages interactive sessions a lot. So with that, over to you, Professor Mistry.
Thank you. Thank you so much. Can you hear me?
Yes,
Yes, sir, you're audible.
Hello?
very good.
Yes. Yes. So I'm very happy to be invited here today for several reasons. Apart from Celeritas and the Sigma Phi Society, I am very happy because our physics department has met the challenge of the pandemic lockdown so beautifully with virtual sessions, projects, exhibition, practicals, and various science programs. I'm in touch with them through the Board of Studies and Academic Council, and I know that they are working hard even under this situation. The fact that they had simulated practicals and so many other things. So thank you very much for inviting me. My journey in physics, the title that I have been given, is closely tied up with my teaching experience and association with colleagues in St. Xavier's College and the university and various other programs at national and global level, which I will mention briefly as I go through my timeline. I would like to share my experiences in terms of a timeline from school to teaching and retirement, etc. And also, time permitting, show you certain motivation points and events which made me love physics more and made me more and more excited even today. So that's the plan of this about half an hour to 40 minutes. If you can see my screen, I want to start with what happened on Sunday whilst I was finalizing this talk. One of my old students, BSc, MSc student, Chintamani, some of you may know it, the teachers may know him. He sent me a picture of the Mars-Moon occultation. And here it is for you all. Let me know if you can see it.
I think your screen is not visible. You're not sharing.
No, I am sharing. I was sharing since long time.
Can you try sharing again?
Okay, present now. So it must have gone off again. Okay, entire screen. Tell me as soon as it comes.
Yes, I'll let you
There
know.
it is. Okay, I've said share. Let me know when it comes. I've kept my video off because otherwise it's becoming even slower. I would like to keep it on, but I don't know.
I think you're not sharing it. Okay, one sec.
I am following all the instructions. It's
You're
only a
sharing
time lag. We should have done it in Zoom. This is taking.
It has
Okay,
come.
can all of you see that?
Yes, sir, it's proper now. Yes.
Okay, so this is the moon. This is the moon, and I'm going to enlarge, and that will take time again. Yep. Okay, there you are. Can you see it?
Yes, sir.
Can all of you see this rectangle?
Yes, yes, sir.
Yes, we can.
Can you see this red rectangle?
Yes, sir.
Yeah, this is emerging from the moon. And this is the from behind Mars. That's the occultation. Like an eclipse, what we talk about, sun and the moon, etc. Here, the major planets and moon occult smaller stars and smaller planets. So here is Mars just emerging. Can you see that? Where my arrow is. And that's few days, April 17 in the evening. And a little later, few minutes later, it has gone here and here. So this is the track of Mars and the moon as two bodies, one overlaps the other. Now, why am I showing you this? Because throughout my physics teaching at St. Xavier's, we have been very, very interested in astronomy and astrophysics. You all realize that here is a subject which takes you into the vast cosmos, and studying physics with astrophysics as the background is a very, very interesting thing which gives you surprises every day. If there is time, I'll tell you something about the most recent surprise at Fermi Lab, which has upset several people about the theory of physics. But there are surprises at every turn. Just few years back, 2016, we had the black holes colliding, and a beautiful experiment, one of the best, I would say, for human ingenuity. We'll talk about that also. So I am touching upon astrophysics and astronomy as a way to be motivated before I show you my timeline. Okay? So let's now look at another part of my screen. Tell me if you see that, and that's the graph which I will leave on for some time. Can you see it?
Yes, sir. It's visible.
Yeah.
Akshita, I would like you to say immediately. That's fast. Okay. So this is on a piece of paper next to me, so that almost like a blackboard, I'm showing you my lifeline in physics. Okay. So let's go fast. And in between, there will be some points where I will show you something more. Just now, when I was introduced, people talked about founding of AAA, Amateur Astronomers Association, not Alcoholics Anonymous. And you will see some other interesting things also. After I finish this, a couple of questions, and then I will give you some higher motivation, which I, as a student and teacher, did for myself to get more and more knowledgeable about physics and therefore teach it better. So here I am from school, St. Xavier's High School. Can you see my green arrow?
Yes, sir.
Okay. The shaded portion is college. And I am now retired. Can you see that? Okay. So
Yes.
the timeline, of course, is below.
Yes.
The timeline 2020 is here, going on to 2030. I retired at this point. And as you all know, I'm still with physics, with Xavier's, and with media. Okay? So what happened as I came from school? 1964, I walked into St. Xavier's College, FY BSc. At that time, it was FY Inter-Science, Junior BSc, Senior BSc. My first motivation, and please pay attention, was whilst I was a Junior BSc, I asked my head of department, Father Bonet, a Spanish father, whether he would allow me to attend TIFR Cosmic Ray Conference. And he said yes. So I sat there in the last row of their main, not the big auditorium, but the main theater. For those who have been to TFR will know that, and attended every day of the cosmic ray seminar, and I took notes and discussed, and this is 1967, and I'm still in junior BSc, which is the third year of college. I was thrilled to be amongst people who were Nobel laureates and people who had made cosmic rays, in the sense that the study of cosmic rays. People who had done the experiments, people who had done research, and they were talking. And for a young student, it was a tremendous motivation of a high level. In the meantime, other things happened. So you see these arrows coming, and as I go into MSc, PhD, and retirement, you will find some other things happening on the scale of the time axis, okay? So 1968, centenary year for St. Xavier's School and College. I graduated, and 1969, I started teaching as a demonstrator in physics. At that time, there were demonstrators and professors different. 1970, I was made permanent. And within 1 or 2 years, I got into the lectureship. Professor was not that great till just now, 2010 and so on. So till I retired, the highest grade was a type of lecturer or reader. Professor, assistant professor came in just now after 7th pay commission. So all this time, I was with the post-MSc, postgraduate, and I was starting to teach from here. Can you see that? 1969, 1970, and I kept on teaching till I retired in 2007. That's how the 38 years happened. And then, of course, I was already doing some industrial consultancy and XIC, and what I'm not written here, even XIM occasionally, so that on campus I was quite busy. Let's see some of these points. KLK, Kamat, Professor Kamat, my head of department, Laputra, a French professor, and Keller, an Englishman. This is the Kamat-Laputra-Keller plan, which some of us in physics department worked out in the year 1977 onwards. It was a self-paced self-study, and except in US, Keller plan, and in France, Laputra, where Professor Kamat had gone and got the ideas for us, nobody was doing that. It was a unique self-paced self-study plan for the students of physics. Then started the honors program, which many of you are aware, which also I was involved in starting, and there were projects, wonderful projects. But in between, there was something else. Look here. COSIP was College Science Improvement Program of the university. And when I had just joined, the head of department then said, go ahead, teach differently. Because COSIP allowed us to go beyond the syllabus, beyond the practicals. And I have no time just now for detail, but I started teaching differently. The practicals were made completely different. They were not from the book type. They were part of physics, of course, but learning differently. At the same time, somebody from TFR came, and at that time, the principal, by the way, I've been through about 9 principals, came and called me for lunch and said, so-and-so wants, I can give you his name, Dr. A.V. Padankar from TFR, why don't you start a creativity scheme? And this was wonderful, and many of my past students will remember that for 4 years, I did a creativity scheme where students were challenged with projects which were very high level. Okay? This can all be discussed in question answers later. At the same time, we started Khandala seminars. Have you been to a Khandala seminar? Not this year and not last year, but some of you, if you are in TY, may have gone. We have the Xavier's Villa, and every department goes for a seminar with presentations of very high level, but we bond together in the villa in a different atmosphere. Unfortunately, because of the pandemic, last year and this year is not going to be possible, but that's what we started way back in 77 for the staff, full staff. And much later, it was for the departments, and now every department goes. So please remember, my starting was with this cosmic ray, where there were very senior scientists and another inspiration. Immediately on taking over, that is lectureship, I had a lot of possibilities of attending things. Now please look how MSc was done. Can you see this? Before the university was established like it is today, Kalina was not there, campus. We had 22 professors in 2 years from TIFR to BRC, including Bhavan Zanderi, including Xavier's, including Khalsa College, including Institute of Science. Can you hear me, Akshita?
Yes, sir.
Okay. So please see, MSc was a different cup of tea. The whole student batch had to move around Bombay because there was no central Bombay University MSc teaching. But it was good, it was difficult because the practicals were done in your own college, Xavier's, and then you had to run for morning lectures and evening lectures to all these places. But we had the top professors, the very top professors here from all over. You see that little bump? So in 1975, I spent 6 months in London University, as a special grant for physics teaching. And I utilized that time because they sort of, it wasn't a huge payment, but whatever small weekly payment I had to save and travel all over and study. So I went to so many conferences in United Kingdom, including solar energy, including what is called the Nuffield A-level physics, okay, which is equivalent to InterScience or 12th standard here, but is one of the world's standard physics courses, Nuffield, Nuffield, after Lord Nuffield. So that changed my thinking. In fact, I got this award because I attended at Aligarh Muslim University a 2-day conference on teaching physics. From there, they elected me and I went there. I learned a whole lot of physics training there. I made videos there. This is 1975. And then, much later, I started my PhD at Baba Atomic Research Center. I'm going to tell you about the PhD a little later. So this is the story of sort of physics journey up to PhD. In between, many, many things happened because as you see on top, which is hidden here, all this was teaching and research. I did my PhD not completely in BRC, but taking lectures in college, finishing them, rushing to Baba Atomic Research Center, coming back, spending the night. I had experiments in the physics lab overnight. In fact, people from Baba Atomic Research Center would come and visit our lab when they saw something very, very new being done. This was on lasers. By this time, I was hooked on optics and lasers, and therefore much of my work was on spectroscopy. Okay, which still, of course, some of it carries on here after retirement. Now, just 2 more things or 3 more things before I go to certain events. The total solar eclipse, 1995 and 1980, both I organized through what is called the AAA. You saw that. AAA is the Amateur Astronomers Association. So AAA 1980, the group went to Karwar in South India, and 1995 AAA group, which is of course care of physics department. AAA was at that time care of physics department. And we went to Andiari village. I'm talking now of October 1995, 24th October 1995, because I'm going to show you pictures and I'm going to show you certain graphs which we plotted. There were about 40 to 50 people, including scientists, teachers, students, and a few public people. Okay? So that was a real motivation and an education to actually see an eclipse and measure parameters like temperature, humidity, light, something about human blood count, and also radio waves. So all this we did after practice of 1 month in Xavier's on the terrace of the hostel. We did some trials, and then we went to Undiari village near Agra, where we stood on the center line of the totality. For those who understand totality will know that the total eclipse is seen in a narrow path. If you go out of that, the eclipse is no longer total. Okay? So I'm going to show you a few pictures of that. In between, please see here also that whilst I was teaching, the metro TBM is tunnel boring machine. I was very interested. And this is my engineering background and interest, because my basic interest is also applied physics. And throughout my teaching career, I had to apply and tell the students what really physics in daily life means. And I don't know how many of you have bothered to study how the tunnel boring machine works, but years back, one of my students was with a German firm, and the tunnel boring machine had come to Worli for the Worli gutter tunnel, which at that time was taking the dirty water, from the Worli gutter 3 kilometers into the ocean. But now, of course, this metro is different. So I studied it thoroughly. I was involved with the Bombay Metro through another small project. And I got full details of every single thing about the metro and the German machines, the Chinese machines and all that. And I taught that to my students and made them interested even after, during the retirement or just before. Okay? So this is the story of going from school right up to XIC. How did XIC happen? Now that's interesting. When I was vice principal, that is somewhere near 86 to 94, I started audiovisual training of the teachers. And for that, I required help from XIC. So with the help from XIC, I taught some of our teachers, and you would be very happy that we actually made movies for Doordarshan, what UGC Doordarshan, which was called the, what was that in those times? Countrywide Classroom. Yeah, it was called Countrywide Classroom, and they were about half an hour duration videos of very high level. I made one which was called Laser the Wonder Light, which is still very popular. Technically, it is not too good because it was shot in BRC by cameramen, but the complete subject expertise and the details were made by us. Some of my students are also there, and I can show that to you in the copies there in the college. So XIC link started. In between, the XIC then director asked me, why don't you teach computer graphics and animation? And I had just come from Lucknow after a laser seminar, and I had seen there, Kanpur, IIT Kanpur. I had seen some of the best graphics being done there, but that was old. I'm again talking of early, before 1987 or so. And then I started teaching here in 1991 after preparing myself. And that is what, when I was introduced, it was said this was the first time that computer graphic and animation training together with nonlinear editing was done. Let's now jump and go. So 3D CGA, three-dimensional computer graphics and animation. Can you read that? And nonlinear editing.
Yeah.
This, and of course, now I teach photography. I've conducted about nearly 50 courses. 38 of them are for the public. The others are for diploma courses for the XIC. So I am very fascinated by photography. And if you see all this, underlying my background is optics, lasers, and spectroscopy. But in between, I made myself experience in electronics. We were the first college to introduce microprocessors and training, 80, 85, 80, 86, even before the university. We were the first to introduce lasers and fiber optics before the university. So all this was Xavier's. Before being autonomy, we were doing all this, okay? Now I want to change the scenario. And so this is gone. When I need it, I will use this. And by the way, I'm using my mobile camera as a second camera, and my webcam is what is looking at me. Let's now go to the main things here. I hope that doesn't take too much time. All of you watch. So now what you're seeing are things which motivated me beyond just the textbook. Okay? And those of my students who are or were with me know that very often these things excited them much more than just the curriculum. Okay? Now, can you see Earth? Can anybody see Earth here? Chashma saaf karke dekho. Well, I'm going to show you. Voila. Can you see that? Can you see Earth, please?
Yes, sir. Yes, sir.
Somebody else.
Yes, sir.
Yeah. Now, Earth is being seen through the rings of Saturn. So, who was photographing it? Well, the US spacecraft. One of them is many of the Voyager Pioneer which went through. Now, I want some of you students to just go home and write down and find out on the web what is the reference pale blue dot. Anybody knows?
Yeah, Carl
Yes,
Sagan.
sir.
That's right. Very good. Carl Sagan from Cornell wrote a piece called The Pale Blue Dot, and he meant this type of picture. Please, all of you, for a moment, think of all your ego and all the economic things and status that we have, and all of us are just bundled in this small dot. How big is this dot? Insignificant. In the solar system, small. In the Milky Way, insignificant. In the universe, absolutely insignificant. Do you get it? I show this picture very often to teachers also to sensitize them why the earth is just our only plan for life till we find something else or we find another civilization. I'm going to a better picture next of the same thing, the pale blue dot. You must try and see what these pictures mean, how they were taken. Can you see that? Another view of the Earth through Saturn's rings by a spacecraft which has left Saturn. Can you see it?
Yes, sir.
Yes, sir.
So this is the beauty of astronomy and astrophysics. I'll go down to engineering and other things later, but please watch. Okay, I mentioned that we did a small project on comets. Yes, St. Xavier's College Physics Department with AAA. This is Comet Halley. I saw it and photographed it in 1987. This photograph is not mine. The photograph which our group did, we wrote a paper on it by actually measuring the head of the comet, the tail of the comet, and the speed of the comet. Okay, and that was fantastic. How we did that? We had a Norton star chart by which very accurate star positions are known. So behind, if you can identify stars when you take the comet, and I used a densitometer to study this and found out the diameter of the head. The paper is there with me if anybody is interested. We found out the length of the tail and we found out the speed. Anyone can tell me how do I find speed of this comet? This comet comes 76 years interval. Come on, please respond fast. Please respond. How does one measure the speed of the comet? Can you hear me? Hello?
Yes, sir. You're audible. Yes, sir.
But respond very fast, please. So long kaise hota hai?
So there's
How do you measure the
answer in
speed of this
chat.
comet?
So there's an answer in the chat. By measuring
No,
how much
I
it
cannot
moves
see.
relative to
No,
the
no, I
mass.
cannot see. That's right, that's right. But I cannot see chat because you see the timing is so that I can concentrate on what I show. So I can answer the chat later. Better to answer immediately. The answer is correct. If you measure with a standard atlas known stars, and we took half an hour to exposures after half an hour, so that was the movement in the sky in terms of angle of the comet. We took the distance of the comet from data which was coming from NASA and others, and measured the movement and found out the speed. All this is recorded and we gave it as a presentation. My partner was Adil Desai, not of Xavier's, but very much of AAA. He was secretary of AAA. So he took the picture and I did the analysis here in our physics department, and we both then presented the paper. Let's go ahead. This is a fantastic scene from the web. This is Comet Halley going into the Milky Way. I saw it first time last week when I was hunting for some beautiful pictures. We always see comets like this. By the way, what are these two tails? Respond, please. Hello. Why does the comet have multiple tails? Well, I'll tell you, one of them is the ion tail, gas ion, and the other is the dust tail. Are you listening?
Yes, I am.
Yes.
Yes, I am.
Okay. So I'm going to show you the head of this comet, which is very, very small, rocky, icy, extremely small. But this itself is nearly 1 lakh kilometers. And by the way, the tail, we calculated a few million kilometers. Okay? The full tail. I was studying black and white pictures on a densitometer, Carl Zeiss densitometer. That's how we measured it. Now, my asking of these two tails, you see the comet shines because the pressure from the sun, radiation as well as other emanations from the sun, cause the flow of the material out of the comet. The gaseous material, which is ionized and has a color, sometimes pink, sometimes blue. Please look at the web, you'll find beautiful comets since time immemorial, all with different colors, shapes, including one big comet which broke up into 9 parts as it passed near the sun. Okay, so this part is just dust. And this is like mechanics. So the particles are blown backward. Okay, but as the comet travels in an ellipse, remember it's an elliptic path, this doesn't trace a straight line from the sun, but this does. So the sun, if you want to know, is here and not here. I hope you're getting this. So the dust behaves in a different way, the tail, and the ion tail, ION, the gas ion tail, glows because of its excited molecular ions. You can find out what ions. We have spectroscopy for that. Okay, let's go ahead. This picture is simply marvelous because the Milky Way, you know, is made up of millions of galaxies and stars, and the comet is a visitor which goes past somewhere and back again. Okay? It's just that the Milky Way background looks so beautiful. And now I show you the head of the comet. This was taken, I think, by the European Space Observatory satellite. And this is just a stone, like a big chunk of a star, asteroid. Some of it has icy material. By ice, I don't mean H2O ice, but solid CO2. And this is part of the emanation which forms the tail. This is a very, very high resolution picture. So that's what excites us into physics. Let's go ahead. And I promised you the total solar eclipse. This is the diamond ring. This picture is from the web. I have my pictures, they are on slides, and I can actually show you later. But I have seen a prominence from here, which is at least 10 times the size of the Earth. So on the scale of the sun, By the way, the moon and sun have the same angular diameter from Earth. That's why total solar eclipse happens. But when the eclipse happens, you see only those little, some of you can see something here, right? This is the last part of the sun, we call it diamond ring. Before it disappears and the moon comes this way, here is the total solar eclipse. Beautiful, absolutely. A lot of physics. This is the north-south pole. You can see the lines. This is known as Dahlia petal. So this is the corona, the crown of the sun, and this is the last part of the sun being covered. For those interested in optics, there's also chromatic aberration here. And this, can you see that? Can you see the prominence here? Please say yes or no.
Yes, sir.
Yes, sir.
There is a long outshoot of solar plasma coming out. And believe me, the earth would be simply roasted, toasted, completely vaporized if it was here. That size of the earth is just tiny, okay? Now the last scene is when it goes the other side. So you have seen that the sun and moon go across in a line. The earth is the observer, the moon comes in the middle, the sun is here, it gets covered completely, and at that moment, and I have written articles on how to photograph the eclipse, it is simply fantastic. You have to be ready, it takes a few seconds, takes a few minutes, but it is centuries apart that you have fantastic eclipses, okay? So this is 1994 eclipse, but the pictures are not mine. I have pictures here, okay, I'll show you right now. They are on print because I was using film with my Spotmatic. Can you all see this at the side?
Yes, sir.
Okay, so that's my second camera and I'm blowing it up. That's my picture. Okay, and it's not very clear here. I'm just using LED light to show this. Here's another picture. And if you are careful, you can spot that same prominence. Some more. So these are the actual pictures taken with Spotmatic Pentax camera, 100 ASA film on a tripod and a 350mm Solicor camera multiplied by 3, okay, with a telescopic arrangement. So I was working with a 1000mm telephoto. At that time, this is 1995. Okay. Now, here's the diamond ring that we got. It's called diamond ring for obvious reasons because it looks like a sparkling diamond. And here is another one. So these are all our pictures. They aren't good because they are now very old and shop soil and it's shining from top. But my slides are there and those are still very, very clean. So this is all about eclipse. Okay. I'll push this out. Let's go ahead. Okay. I've kept this as a stop, reminding me that I'm going to show you something else. Please bear with me because Rajesh Singh, are you there? In the previous Prof magazine and other things, he has used my graphs on the cover. Some of you may realize. Please have a look now. This is something worth. Can all of you see this?
Yes, sir.
This is.
Yes, sir.
I have plotted this on huge graphs. This is just a quick way of showing it. But this is what we did, please. 40, 50 of us trained for 1 month. We went to Anjari village after studying all the logistics. There was no GPS. This is 23rd October. Those who do a solar energy project, TSC, total solar, always have to take before and after to see how the sky was and then the eclipse. Here's one day before. Same time in the morning, the eclipse will happen at 8:30. The sun rises. Can you see the red line? The temperature rises. The blue line, light increases. And percentage humidity, violet line, is the humidity. Now, you'll get a shock as to see what happens now. This is eclipse time. And I'm going to show you one at a time. What does this graph tell you? By the way, this graph is plotted and smoothed, but it actually points. We've got hundreds of points here. Students are all assigned. So totality, and this is light. So the light dips. Compare it with the previous graph, which went like this. So at 8:30, the graph dips. And now we are looking at temperature, right? So let's look at the temperature. I'm sorry, this is humidity. So when light goes down, remember 8:30 in the morning, the sun has been eclipsed, it's dark. You can see planets. At that time, the humidity rises. Now there's a lot of physics here. Please see the out of phase between light, humidity, and temperature. Can you make this out?
Yeah.
Can you see that the temperature reaches a minimum a few minutes after the light and humidity? Why?
Yes.
What's the physics? Temperature is a macro slow phenomena. Light is instant. Light can be shut off and put on. Temperature and humidity are macro phenomena which require kinetic theory and mixing of gases and equalizing. So the temperature effect is a little slower. Now, I don't have it here. We did a radio astronomy first time also, and lots of other things. We had doctors with us checking blood samples, people looking for reaction of dogs, cats, snakes, because we were out in wild country. So this is to tell you the beauty of total solar eclipse motivating you for. Here is the 1980 report, February 1980 from Karwar. Same things, okay? The same type of plots were done. I trained them, but I couldn't go due to personal reasons. But all this was done, and this was in the evening, 4 o'clock. Okay, a full report on 1980. This is Physics Department, AAA, amateur astronomy. The recent report which you saw was 1995. Let's go ahead from here and see something else. 1 minute, sorry. Now, this to me was the greatest excitement few years back to study physics more and more. This is the famous LIGO laser interferometer experiment in United States. And how many? Okay, many of you must have seen it. How many of you have studied it? It would be great for a project. Please, I hope it's working. 1 minute. I'll put on the video and sound. So those who have seen it will realize that the mathematical modeling of two black holes rotating and collapsing actually gave rise to variations on an interferometer on Earth. Let's hope it opens. Okay, here it goes. Pay attention. Tell me if you see it when it comes. Here it is, please pay attention. Can you all see it?
Yes, sir. Yes, sir.
Okay. Okay. laser interferometer gravity observatory, 2,000 kilometers distance between Hanford and Livingston in United States.
Yeah.
This experiment to me is simply, can you hear me?
Yeah.
Is simply beautiful.
Yes.
People have recorded gravitational waves, and the way to record it is by an optical interferometer, one of my most favorite subjects to teach and to study, including in my research. So 4-kilometer arms, beautifully suspended mirrors, neodymium laser, and perfect electronics with a lot of understanding of any other parameter. In fact, these two signals are correlated even though they are 2,000 kilometers away, and therefore it's about a few fraction of a millisecond speed of light takes. The speed of gravity waves is the same as speed of light in the sense that they affect in the same way, and there was no doubt that this was gravity waves. And if you still doubt, I'll show you the next one if you've not seen one. This is the actual modeling, mathematical modeling. Mathematics goes hand in hand with physics as a tool for modeling and finding out, predicting things, etc., just like computer science. So here is the actual modeling of this signal. And the match was so perfect that I take my hats off to the people who worked. For those of you here in the audience who have not seen it, go to the web, type LIGO experiment, and please study it. Two black holes, and you know what a black hole is. They are moving together in their mutual gravity fields and will collapse into one. That causes the fabric of gravity to change. Please watch. I'm going to ask a question, stay ready. This is a mathematical simulation of the actual experimental analysis signal. Tell me what you see, any one of you. There's a direct correlation between what you saw and the signal. People match their feelings perfectly of what was happening. So what did you notice? Anyone? This is part of your syllabus at TY. What do you notice? You see that they are going faster, and therefore the signal on the side gets higher frequency, and then finally becomes one black hole. This phenomenon interferometer to change by a millionth of a hair thickness, and that did it again and again, all these things, and when they were ready, this phenomenon happened. What? Do you all know what is gravitational lensing? When massive gravity is there in your line of sight, the background stars, their positions are deviated, are deformed. And it's happening here in this model, but it happened in actual life also. It's called gravitational lensing. I have no time right now to show you, but it's like a convex lens, and you see the image where it should not be, and it's due to gravity bending space-time and light in a certain way. Okay, so that was it. Let's close this, go ahead. Just a few more visuals, and I'll conclude. Okay, yesterday, since we are in lockdown, my wife and I look at various things on the YouTube. And this is physics for me, this is physics for you. When we say that what motivates me, here is a 2.28 lakh ton Star Cruiser type of ship. It carries has 2,000 workers, service workers, plus the staff. And it's a masterpiece of engineering. For those who know that I worked on seat belts and automobile crashes will realize that my interest in this is putting physics to application. 2.28 lakh tons, the front and the back. And I found out 2 days ago something new. We are always finding new. The propulsion of this huge ship is by 3 propellers which are rotating. Can you see this? Look at another view, close up. This is the first time I realized, because I'm not in this field, but I'm ready to understand that instead of rudder and the standard propellers, these 3 propellers swivel and the boat can go whichever direction you want. Okay? So this is the giant strata cruiser. This is the control section, completely automated. The captain is here. In his hand, he has just 3 rotating knobs, just like the jumbo pilot has 4 engine sticks to increase or decrease the engine speed. All he does is rotates those 3 things I showed you, the propeller mounts underneath, and that makes this ship turn and move very fast. This ship can stop in emergency within 3 ship lengths. Do you understand what that means? A ship of this size can stop, even your car can't stop in 3 lengths of car at high speed. So in the ocean, it can be braked and stopped within 3 ship lengths. The length of the ship is 381 meters. The width is about 69 meters. This is gigantic, and it's physics and engineering all together at every stage. And this is something we could work on. This is something we could like to see. Now, since you talk of seatbelt, let's see something different. I'm showing you a car crash. And I've gone through all this because of we'll get the sound and all in this. In fact, this is towards my end where the industrial application of physics is shown, which I actually did for years together, side by side with my teaching and study and research. Just let me get this going. Okay, here it comes. I put the volume high. Enjoy. It's Toyota 2 cars being practiced. In slow motion. Now you might be surprised how I got into this. One and the seat belt, the blue car is crashed, completely crushed. There are high-speed cars, and we have this facility at Pune where I've done a little bit of testing. What I'm showing facilities in India now. I wrote the specifications for seat belts way back in mid-70s. Said thank you and put it in the cupboard. It's only when India started getting cars from abroad with all out, and they established in Pune ARAI, Automobile Research Association, with them, and we set the specifications. Now, let us look. Please, I don't know, I'll have to, okay. Can you see this? I'm showing you parts of the seat belt which we have designed. Can you see it? Please respond.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So this is chrome steel, hard steel. This is the buckle designed by us. This is one of the most sensitive parts which saves the life, and it is purely inertia, spring constant, and physics. If you see this, this is what stops the wheel from letting out the belt if you go fast. The acceleration of this spring was calculated, and this is the buckle. Okay? These were the first belts we made, not the inertia wheel. And here it is. This is the type. You are familiar with this buckle. It's called Bond Safety Belts, the company for which we consulted. And we had to calculate the exact load bearing of this. We had to break several, test several, and finally come to a design which was unique. Not only unique, but even the stitching, the thread, and even these little triangles. This is very special high strength steel. Even this belt buckle. So this is the beauty of research in the industrial background, okay? So this, I'll stop now. Let's see. Okay, I finished most of this. I will not show you here, but please take it down. Go Walter Levin. Professor Walter Levin. Okay? That's his book, and that's him. For the Love of Physics. This is the book. Okay? You will get on YouTube his teaching videos, which shows how committed a good teacher can be and how students would love actual demonstrations. Throughout my life, I've tried to demonstrate either physically or on computer by simulation and by actual. So I have several interesting. Let's see if it works. He's following simple pendulum law. There's a 12-kilogram metal pendulum with him. It will open. In front of him, in MIT, there are top professors and students. This was his last lecture. He retired. Please try Comfort of Home on YouTube. For the Love of Physics. He's got all the physics things explained. Mechanics, optics, electronics, by very interesting experiments, which he himself does. He's going to leave this cannonball. It will swing across the whole theater, class theater, and come back. Watch. It should come here.
Yeah.
There it is. Please watch. Did you see that? Once again, it's a GIF file repeating. It's fun to watch the actual video because he says that if I make a mistake, this is my last lecture. He's standing against the wall and physics works because normally the ball would come back to the starting point. It doesn't because of friction and air drag, and therefore he's safe. 12 kg ball would have smashed his skull.
Correct.
Just before that, he shows how it can break glass. Okay, so that was interesting.
Please hold on. I think Mistry sir has a network issue.
Akshita, can you call him?
Yeah.
He will join back.
Yes, sir, you're here.
Okay, fine.
Yeah, yes.
Okay, so now I won't share. Let's just finish the talk by concluding and a few questions. So if you went through or paid attention to what I had said, we talked about the timeline, okay, from school to college and retirement. Why physics I love is because not only is it fascinating, it is extremely powerful. And there's nothing like old physics because new things are coming on every day. Okay? It is a tough science. I mean, it's not easy to understand it. I wasn't the brilliant student, but I struggled, I understood, I studied from several books to make it interesting for the students. And every time giving examples like I gave you, okay, anything which was intriguing in technology, find out the physics behind it. Whether it's a mobile phone, whether it's a camera, digital camera, whether it's a ship or the airplanes. Airplanes fascinate me also. Think of how the Airbus A380 flies. Okay, look at it, tremendous power and the flight and navigation that is needed. Anyway, about my earlier things, I just want to close by saying a couple of things which helped me. One was the industry, and it came just by itself. Both the industry chances came from the people who wanted me. One of these guys said, can you help me designing the seatbelt? And it was from scratch. Let me tell you, one of the experiments I did was I used one of my then students, who is now PhD and was in US for a long time, as a weight. You know, one of the conditions for seatbelt is that after an accident, the parents should be released by a small child. Do you understand what I'm saying? The seat belt should not lock up after an accident, otherwise you're gone. So I made this boy hang onto the seat belt, and then I measured by putting milligrams and grams at what stage I could release it. And he fell down on the ground. So there was a lot of fun, but these were the crude experiments we did. And I actually wrote the specifications, and the Indian standards wrote, thank you. As I said, shared it in the cupboard for a long time because Indians don't believe in standardization. Till force get the external one. So now you know that without standardization, you cannot sell anything. Okay? So industry, there were two what should I say, excitements. One was seatbelt, which is purely physics and mechanics and, you know, all the things related. The other was quite new. It was digital cinema. I worked in digital cinema for digital projectors, the best in the world, and digital signage, and had a chance to go abroad, actually see how this was done. By the way, when I was doing seatbelt, I was taken to Florida to see the airbag. We didn't design the airbag, but the airbag is another cup of tea. I'd like you to please think about the physics. It's an actual explosion like a grenade in an airbag. And the danger is if the airbag doesn't give, you will kill the person. Do you understand? Children are not allowed to sit next to the airbag because it gives a punch which kills the person. So the adult has to hit the airbag and it has to release in a certain method. These are not simple things to calculate. But, you know, if you have a training in physics and mathematics, and now computers more and more, then you know that all these things have to be designed to perfection. Okay? So I just wanted to impress upon you that the motivation is not just from the textbook. Yes, it is from a good teacher, professors, also from my students who show their eagerness to learn and who come to me again and again for projects and improvements. Okay? There are other things, but one you will like. Many years, 2000, I think, there was a seminar, and I had to talk on the role of physics in national security. Okay, what do you think I would talk? This was an international seminar at Nehru Center, but we were talking mostly about national security, your nation. I gave the full example of United States. Some of you may remember that United States at that time had what is called the Star Wars program. Anybody remembers? Elvin? No?
Yes, sir. Yes, sir.
Just by reading, I mean, yeah. So the Star Wars program was started by Ronald Reagan, who was actually a cowboy president of USA, and it was developed to such a level. And why was I interested? Why was I asked? Because my field was lasers. And the Star Wars worked with a jumbo 747, which opened out its nose, and a hydrogen cyanide HCN laser would go for thousands of miles and disable the enemy missile before it left enemy ground. Do you understand what it means?
Yeah.
So not Star Wars the movie, but Star Wars the program. It was called an anti-missile shield over USA. So I gave a lecture on that, and it was very, very interesting. There were others also. I was just at this particular point. But when a laser weaponry, okay, so it's not just for target and on-ground designation with also shooting satellites and disabling them when they are almost 5,000 to 6,000 by attending. And I attended myself. Nobody sent me. I just attended because I was interested. And my laser frequency stabilization, which is my PhD. I'll just show you one small thing which might give you some idea of what type of work it was. All of you know that we need high resolution, correct? In spectroscopy and in signal processing. So first is, and this is lying in the physics department unused, I made, okay, I have to go to the, anyway, I think I'll show you straight, that might be better. Here you are. Can you see? This is Fabry-Perot rings. SYTY should know that.
Yes. Yeah.
So I made a scanning Fabry-Perot. And it's beautiful. See the resolution. And this is a helium neon laser showing you peaks, what are called modes. But that's not my research. That was just part of it because I had to make things to see my own results. Okay. Now comes the real thing, which is extreme high resolution and frequency stabilization of a laser. And you will wonder how beautiful physics is because I ended up by looking. This might be difficult, but I'll show you the trace. When you see this last pattern, there are nearly 23 peaks under the Doppler curve. Do you know what is the Doppler curve, anyone? Any line of a spectrum is broadened due to movement of the molecules and atoms. Okay? You have a smooth Gaussian type, you know? But in that Doppler curve, hyperfine structure, some of you must know what is hyperfine. Do you know what is hyperfine? Spectroscopy, Veera Shankari, your subject?
Yeah, there are people, they will answer.
तो कोई करता नहीं है. Okay, this is the famous lamp dip. And to see these people from PRC had come to see in our lab. The lamp dip, Willis Lamb, Nobel Prize winner, his photo is there in your TY lab. And this is how I got it. So this is a Doppler curve. Doppler curve means it's a Gaussian. And it's because particles are moving XYZ, kinetic theory. Now see what I did. Within this Doppler curve, I got peaks. Can you see these peaks? 23 peaks like this. And this is hyperfine structure due to the iodine molecular component interacting with the spin and magnetic effects of the electrons. Okay? So this is the combination of the moment of inertia of the nucleus of an iodine molecule, diatomic, with the outer electron shells, and that gives you hyperfine. Please, this hyperfine is something to think about. None of you, if you look at your sodium doublet, will really see a thickness. Correct? A line is a range. Not only have I extended that line of neon, but in that the iodine hyperfine structure has been identified. That's not. I was to stabilize the laser on one peak. Okay? So from the 20, 30 peaks, I had to select one peak. I had to create those peaks by movement of the piezoelectric transistor mirror of the laser and lock it on. And when I locked it on, one of the things of my result was that I would bang the table with a hammer. It would unlock and lock itself. Why? Because there was a feedback loop, electronic feedback loop. I was using a lock-in amplifier, signal processor. So these are fascinating things. And none of it was in the syllabus. And all this is going beyond. Today, much of it is in the syllabus, please. Signal processing, SNR, signal noise ratio. I worked with an instrument and showed my people there at BRC that I could find a signal which was buried 10,000 times under noise. You know what that means? What is signal to noise ratio? It has to be large, isn't it? I don't have your name, Kshitij Singh. What is SNR?
Signal to
Akshita, you can answer? Yeah, but what does it mean? It means that in your experiment, your signal should be large compared to the noise, correct?
Correct.
I'm doing research. I'm doing research by Ulta. 10 raised to minus, that is 1/10,000th of this noise. And yet, not only have I found it, I have locked the laser on it. So this is magnificent. I mean, it's not my fantastic work. It exists like that, and we set it up. Okay, I worked on the second floor of BRC where there were vibrations. I had to go on Sunday. I had to stop work when the fume hood of the chemistry lab was not working. You know, I had to stop when the BRC buses didn't come because vibrations came up from the floor and they were upsetting my laser. And therefore, I finally got 10 raised to minus 10. That is the quality factor, which meant that my laser would stay fixed at a frequency. Okay, so that is the beauty. If you ask me what motivated me and what I would motivate through this learning of mine and sharing with the students, some of these things I've told you. I'm sorry about the. Somebody wants to blow me apart. The technology was a little problem today. I hope it's not there. If we are physically meeting sometime, all this can be done much easier. But any questions, please? Akshita, any questions, please? I'll be happy to answer now or even later if you give me to chat later. Any questions, please? Come on. I'm glad to see you all. Veerashankar, you can ask questions.
Mistry sir, I just wanted to share my experience. In 1995, our group of some group of students who were in the honors program and me and Father Simon, we conducted the
Yes.
total solar eclipse, partial solar eclipse experiment in Mumbai.
Yeah.
In our
While I was
college
there.
terrace. Yeah.
He was in Andiari, Agra.
Yeah, when you were
There was a trained
yeah.
team on hostel terrace. Yes, very good.
Yes.
Very
So,
nice.
and
In
we
fact,
really
I'll
had a
tell
very
you,
nice experience. Yeah.
and that also with partial. Remember, total experience is something out of this world.
Different.
The
And
sun simply goes.
after you showed the results, we compared both also. The students compared and
Yeah, timing
brought out a
was
report.
very
Yeah.
nice.
Yeah. Yeah.
Very nice. Same thing we did for comic outtake. I'll give you one incident just apart from that.
Yeah.
I was photographing the comet outtake from Urvada, which is the holy town for Zoroastrians. It was about 4:30 or 5 in the morning. I had my this film camera, and one old man turned up. I was with tripod. Who was that old man? Guess. He was the high priest of Udwara, and he came there because he had seen the comet last time. Do you know what that means? Here was a person who was seeing comet outtake 2 times, 76 years away.
76 years
He was in his 90s. He was in his 90s, and this man came at 5 o'clock in the morning. So what his love was, he's not a scientist, he's a priest. his love to see this phenomena was so great that I will never forget that. Okay? People would say, who will get up and what is it and how you'll see the comet, it's so faint. You know, comets are not easy to photograph, they are very faint. But to do that, and this man with me was a great happiness to me. So like that, you know, physics, even totally people who are not interested in physics get interested when something like this happens. Any other questions? So I just picked astronomy, but believe me, it's not my only interest. My interest in lasers, optics, applications is tremendous, including computer science today. And I would urge you all to do a little bit of coding, okay, and try to learn how computers can control things, but don't forget the hands-on experience, because computers can also give you junk. You know, GIGO, garbage in, garbage out. Okay, so mathematical analysis of the wrong data will not give you right answer. You have to be creative and do hands-on physics, because all my life, alignment of optics, you know, most people, you know, would be frightened. And I would do it within seconds, simply because I loved it. And I love to set it right, because if you don't set it right, it's halfway and your results are not correct. Okay, so heat, optics, electricity, electromagnetism, nuclear physics. I've done an alpha particle scattering. I've done so many experiments by myself. You know, nowadays it's not allowed radioactive, but we had a lot of radioactivity.
Sir,
study.
can I disturb you in between?
Yes, of course.
Actually, I'm very much fortunate to have you. I had you with me all the time in TY lab, and you are the person from whom I learned techniques of light single mirror and biprism experiments. Even though I'm totally zero in the theory of optics, but I can perform all these experiments very skillfully and much efficiently than I would have otherwise done if you would have not been with me in the labs.
Yeah. Let me tell you who
Not been with me in the labs.
Yeah. Let me tell you who inspired me. There was a Dr. Prera. Two of my seniors, Professor Kambata was very senior. I mean, he had retired by the time I joined in 69. So they had a love for optics, which they transferred to me. And when you say that I did it easily and well, it was simply a joy to get the fringes as they should be. And I would challenge that what you get in textbook, I'll get better. You understand? So if you see Jenkins and White and this and that, I used to get as good, if not better, because you know that urge was there to get the perfect fringes. So optics was, yes, very close to my heart, and I spent a lot of time. But then lasers came automatically to me, and the first laser which came to St. Xavier's College, it was broken by somebody who didn't know what to do. The next laser came to me for alignment. I aligned it, and henceforth I was stuck with lasers continuously from early 60s, you know, when I was a student.
Sir, recently we did Zeeman effect experiment also. 2 years ago. Zeeman effect, new apparatus. You helped us in aligning everything. Yeah.
I know. In many colleges, Zeeman was never touched because people could not do it at all. Okay? And by the way, I learned Zeeman effect not on the apparatus that we have, old one also. It was Professor Kambata's made thing of wood, what he was doing research with Raman effect, you know. So I didn't tell you, but I did some little research on Nepalese coins. Coins from Nepal, what they are made up of. So I worked on a Carl Zeiss spectrometer, which is there, ultraviolet, and we identified and wrote a paper for Carl Zeiss Journal Review on what is the material in the coins of Nepal. I'm talking again of 70s.
So if I may,
Yeah. Sorry?
so if we could proceed with the magazine launch right now, and then we could open into discussion after that. Okay.
Yeah. Do launch the magazine, otherwise
It's
we'll come for the main thing and we'll forget. So go ahead and launch the magazine. I am dying to see it. You're supposed to give me an e-copy. Send it to me. But right now you can do the official launching.
Alvin, would you like to go?
Yes, sir. Yes, definitely. But before going to the launch, definitely I must say, sir, that your talk was really inspiring. You touched on so many aspects, not just of physics and applied physics, but also delved into engineering, your experience and the old times at St. Xavier's. So it was superb. I mean, the practical apparatus that you showed us about the seatbelts, and then the images of the celestial objects. That was really to you, sir. Of course, we will be open to discussion, taking questions in the chat box and all a little later, just after we come up with Celeritas comes to light. But that was really a good session, so extremely grateful to you.
So
Yeah.
let's launch the magazine.
Yes, sir, yes. So Celeritas is just going to come alive quite soon. And before that, we have Akshita, editorial head of Sigma Phi, to acquaint us with the magazine. Over to you, Akshita.
Thank you, Alvin. And good evening, everyone. It was a really inspiring and motivating talk by Professor Mistry. And thank you so much, sir, for your amazing insights. I was in agreement when Sir said that the promotion of science is crucial to further the understanding of human race. The younger generation should be fascinated and intrigued by all the great science and research happening around us. We at Sigma Phi try to help with just that. Many of our initiatives focus on making students aware of the progressions in science and make them feel the beauty of it. On this note, I'm very proud to announce that we will be releasing our annual magazine Celeritas 2021 very soon. This will be a unique and creative issue with an interesting theme. The fact that it will be a soft copy makes it accessible and easily available to everyone. Before I talk about the magazine itself, I would like to give a major shout out to the editorial team and everyone who was involved in making this possible. I'm so fortunate to have worked with such a sincere and hardworking group of people. The ones who don't shy away from deadlines in spite of academic pressure. Managing both college and society work very well, they continue to bring out excellent, good quality work. And I hope that this is reflected in the magazine as well. I would like to especially acknowledge certain people who were crucial in the execution process. The editorial subheads, Alvin, Rohan, Megha, Aditya, and Ashish. Overseeing the designs and illustrations was Ashya, Roshni, and Hardik. I hope that you all will enjoy the magazine and appreciate the efforts put in. Started to sound like a vote of thanks, but I feel it is important to acknowledge people for their efforts. Great fundamental support has always been provided to us by the core committee and the Department of Physics in everything we do. The Sigma Phi coordinator, Professor Rohan Jadhav, and our physics HOD, Professor Jyoti Singh, have always guided us and supported us in our endeavors. We are deeply grateful for the same. Now, coming to the magazine itself, we felt that it was important to acknowledge and focus on a major change in the past 1.5 years. Yes, the pandemic. The pandemic has caused chaos all around the world. However, it has also taught us many things. It has taught us to adjust with the most difficult of situations and live up to our commitments. This issue of Celeritas is an ode to all those professors and students who tried their best to make the system of online education work. We cover a lot of interesting insights on the same. And at this point, I would like to invite Roshni and Aditya to speak more about the magazine and its contents. Thank you.
Really kind words by you, Akshita, and good evening, everyone. So, this is me, Aditya, and Roshni will be joining in quickly. Regarding the magazine, it was a really brilliant time working with it. The entire editorial as well as the extended Sigma Phi, everyone came together to put across their content and their ideas for this. What was different this year, as Akshita pointed out correctly, that it was all digital and online, and due to pandemic, a lot of things came as a challenge to us. But then again, there was this opportunity to learn from the challenges. So one of the things that we could actually avail was that due to the magazine not need to be printed, it's not on print, but it's digital. That's why we could put into the magazine a lot of dynamic content rather than static content that you would see in print magazines. So we have a lot of communication between the reader and the writer in the magazine that we can put in various different ways. Also, this time in magazine, there was a very big team, which is outside of physics and also inside of physics. A lot of diversity in articles, not only technical articles, but also a little bit of philosophical and a little bit of variety or fun-sided articles. Especially what there was this interesting observation that we made that masters, the MSc students are writing about their complicated relationship with physics, but the first year BScs are writing about Feynman equations and other concepts of physics, which was a complete flip of what actually goes on regarding when we come and study physics. On top of that, a lot of people were able to explore the other sides of their personality and character, like the art, the literature, and everything else. That this time we were able to properly explore that. And obviously we'll be coming to the technicalities of how we manage that and what else was different. There were other things that helped us, like this year, actually from December itself, we were preparing for the magazine in a way. Since Signify launched its newsletter, we have a monthly newsletter, Signify does that. And because of how we were going on with the newsletter and executing it, we got a head start on the magazine on how to implement the work, since the newsletter has almost a similar format as the magazine being much bigger than the newsletter though. So we got a head start. And one thing I would like to really give a shout out on is the art team. This time we have incorporated art in a major way, along with literature as well. The art, because we had to design manage the layout, the technical details, and the illustrations. Since this time we were not releasing the magazine on print, a lot of the illustrations had to be digital. So that we had to learn as soon as possible and implement it on the magazine, and then working with different things for the layout. And for this, I would like to call the incredibly hardworking and talented Roshni. The entire art team was managed, and how it was incorporated in the magazine, and how they worked parallelly with the article writers and literatures and the artists writing about science and physics.
Thanks, Aditya. So I'll actually start from where he ended with the newsletters. So we were a group of just 5 people, and none of us were graphic designers. None of us knew anything about how to do the layout. We were writers. We knew how to write the content. We had that prepared. Then we were like, wait, how do we execute this? And that's when Ashia and I we were just like, okay, what do we have right now? We had nothing. None of us had any experience in Adobe, PS, InDesign, and those softwares. So we just like, okay, we have Word. It's a word processor, but can we do something with it? And we actually pulled off 3 issues of the newsletter, December, Jan, and Feb, on Word. And we came to realize that if we have some basic art skills and some basic organization and how to create the layout to make it visually pleasing and at the same time deliver the content, we can work with the limited tools that we had. But thankfully then Akshita was able to assemble a huge team of artists and illustrators and graphic designers and people with all sorts of artistic talents. And with that came in Shivani and Hardik, and they came in with a lot of valuable skills in Photoshop and InDesign. And Hardik is a professional in the field. He's a creative solutionist, and Shivani is also a graphic designer. And with them, we were able to create more professional layouts with the 4th and 5th issue. And then, of course, we have the magazine, which is our the last thing that we are publishing this year. And I'd just like to say a few things about how we go about with the designing and everything. So creating a magazine is not just about it is the most important part is excellent content, but it has to be combined with brilliant designing and beautiful illustrations and carefully laying out the content in a way that's not only visually pleasing but fits the overall theme of the magazine as well as the specific content that is there in the page. It has to fit that as well. And illustrations is a whole different story. I mean, an illustrator does not just need the artistic skills, but they need to have thorough understanding of the concept behind what they are illustrating, be able to deliver the illustration in a way that the viewer is completely able to understand what they are trying to do. So this is where I'd like to talk about how the collaboration between the author and the illustrator, the designer, is very, very important. The pandemic definitely proved to be a big challenge because we were not able to discuss and everything, but still the online interface, video conferencing allowed us to do that, and we were able to discuss even the authors, the designers, everyone discussed the ideas for the cover, which we will be releasing soon in a few minutes. And of course, everyone's ideas came into the picture, but at the end, it is the designer, the graphic designer, the illustrator who actually executes the final idea, brings together all the discussions, and finally puts it on paper. So I'd like to thank our art team and all the hardworking members of editorial as well to make this collaboration possible, so that we were able to create all these. Yeah. That's all I'd like to say.
Thank you, Roshni, and thank you, Aditya. Good job by the art team and the editorial team. A lot of work has gone in making not just the cover of the magazine that will be released now, but also the entire set of magazine which will be released quite shortly. So Ashia will be actually doing the honors and getting the magazine, unveiling the actual cover. So over to you, Ashia.
Thank you. On the 31st of December 2019, the world was eagerly awaiting the dawn of 2020 to shine on us. Little did we know that on the very same day, a report being submitted to the WHO was going to put the entire world on a standstill. Cases of pneumonia of unknown causes were reported in Wuhan City, China. An year and 110 days later, we have now accustomed ourselves to the new normal, one where breathing fresh air without masks or going about your daily chores with zero hindrance seems like a privilege in itself. Nonetheless, humanity has always emerged victorious in all the battles it has had to face. Celeritas 2021, the annual physics magazine of Sigma Phi, the Physics Society of St. Xavier's College, aims at exploring how the knowledge of physics is being imparted to postgraduates and undergraduates through various modes when the Earth as a whole has been hit by the coronavirus. The cover page of Sigma Phi 2021 is designed by Hardik Kumarwit of SYBSE, and here we go.
Space station. International Space Station. Solar. Yeah.
Is it audible?
No, it's not audible.
It was.
Let's. I'll reshare. Is it audible now?
Not yet.
Zero present.
Please stay tuned to our website, and we'll be releasing our magazine by the end of this month. And thank you so much to we hand the control back to Elvin.
Thank you so much, Ashia. Congratulations, Society of Physics. It was really a good job done by not just physics students, but I would say the whole of non-physics people as well. So it was a good, healthy collaboration. And that was Celeritas 2021 cover done by a good collaboration of everyone. So that almost brings down the curtains to this event. And of course, as is ceremonial, I invite Megha Magakar for the vote of thanks. Megha, over to you.
I think Megha is
I
not
think-
the
Yeah, her network. Yeah, she's now in the meet.
Okay, yeah. Due to some network issues now, that's one of the new normals that has come into picture with the pandemic coming in. So we can't help it. Anyway, so continuing further, it was actually a really good thing. We were all waiting for this day, and at the outset, before thanking the larger audience, I first thank Dr. Jangir Mistry first of all for accepting our invitation, and we were wanting to have a good chief guest and a really prominent person to unveil our magazine, and we had the pleasure of having you, sir. Thank you for that. Of course, your talk, the session was really extremely superb. Apart from that, we thank the entire Society of Physics, all the collaborators, not just our physics students, but non-physics as well, who collaborated and worked on Celeritas 2021. Fantastic piece, and the entire copy will be coming out as soon, as Ashia said. Thanks to the department, the faculty of Department of Physics, and Professor Rohan, who coordinated with the Society of Physics. Their support was needed, otherwise this just wouldn't have been possible. And apart from that, thanking everyone. At present, we have 28 participants, so thanking everyone. And at the peak, we had something around 50. So even at that, we thank everyone for coming, taking your time out, being a part of joining us for unveiling this magazine, which really went a lot, and it meant a lot for us. Thank you. The public relations Jay will be putting up there's a feedback form for us. The link will be put up, and the recording of this event is available on our YouTube channel. So do check it out. The link to both the things will be put up in the chat box. And apart from that, we are open to discussions now with Dr. Mistry. There were a few chat questions which were there during his talk, so those will be answered now. If Dr. Mistry is okay with it. And thank you, sir. And yes, sir. And apart from that, thank you to yes, sir. And apart from that, thanks to everyone for being a part with us. Have a nice evening. Thank you. Goodbye. We are open for discussions now, so the chat box and other general questions can be addressed. You can unmute and have a conversation. The stage is open.
Sorry, I would like to interrupt. So those who have joined, they can fill in the feedback form. It has been provided in the chat box. So yeah, you all can continue. Yeah, sir, you can continue.
No, somebody ask questions, even if they are in chat box, I can't get them.
There was this question during the talk by Nihar Bankudre. Are you still there, Nihar? Or would you want to unmute? Are you still there in the meet?
Yeah, and there's
Yeah. Would you unmute and yeah, you can ask your question. Go ahead.
okay.
Yeah.
So during the presentation, there was showing the graphs about LIGO's experiment, and at that time,
Yeah.
sir showed an image of two black holes colliding. Means, the graphs depict that black holes were colliding.
Yeah. No, what is the
So
question?
that I had read about it on Google, and it was written that the merger of black holes is a ring down of a black hole. So means, can
That's
you
right.
share light on it? Means what actually that term means, and means how those
The
terms
ring down.
arrived?
Yeah. See, so remember there was no actual black hole photograph. That was a model, mathematical modeling, with all the data that we have, plus all the theory that we have. So from the size, distance, and the rotation speed, etc. So it's a question of, two gravitational masses eating into each other and turning round and round and finally collapsing into you saw that it went faster, the frequency. You could even hear the audio frequencies, thin lines, thick lines, etc. as a position, okay? Wavelength, frequency, position. But it has a thickness, and that's where the Doppler comes in. So if I were to see this, in normal terms, it's a Doppler, a Gaussian. What it means is that this is mu zero, center frequency of a transition E2 to E1. I hope all of you know that the line is nothing but a transition from a higher energy to lower energy, or reverse if it's absorption. But why is it like this? Why not a single line? And that's a lot of beautiful physics. Because I had to stabilize that no Doppler effect would do. In fact, my method is Doppler free. Okay? How did all that happen? It's quite involved, but the line thickness can be due to several things. This is laser lines. So it would be the power of the laser, it would be temperature, it would be the movement, the pressure, etc., etc., etc. Correct? So successively, the student asked me, where can Doppler be used? Doppler can tell you the temperature because there is a direct relation with the width of the Doppler line, half width. You know what is half width? It's called FWHM, full width at half maximum. Actually tells you it's a thickness in lambda or frequency or wave number. So thicker the line, there is more kinetic motion. Now you know from let's keep relativity out, but for normal speeds, the speed of an atom or molecule going does not show Doppler effect. Do you understand? If you have like this x, y, z, and z is the axis coming towards you, if an atom is moving towards you, there is no Doppler effect, classical. Do you know what is Doppler effect? The sound, train, whistle, etc.
Yes, sir.
The frequency changes, wavelength frequency changes as it comes towards you or away from you. So x and y axis, you can talk about that. But the z axis, if it is perpendicular to that, then it is not traveling in a way that it is going away or coming towards you. It's remaining the same. So normally the center, nu zero, is that non-moving particle. Okay? This one. When you go on the right, the frequency is increasing. What does it mean? The atoms are coming towards you in the sample. When you go to the left of the center, so left and right center is plus delta nu minus delta nu. Nu is the frequency, okay? And nu zero is the center line. So this is the Doppler effect. There's a direct relation with the temperature, pressure, power. You can find it in the data for a particular gas in a situation at a certain temperature and pressure. Now, I had to frequency stabilize my laser. So I had to cut off this Doppler. And it's not easy to cut off this Doppler. There are several ways. The final way I used, which requires a little bit of advanced understanding is inverse lamp dip. It's also called saturation spectroscopy. In very simple, what we did was, the laser was a single mode laser, very sharp laser. You saw in one of my drawings, the laser is extremely sharp this way, okay? It's not rounded off. So as I move it by moving the cavity of the laser across the Doppler. I found that there are tiny hyperfine structure, which means very, very close, thin absorption lines of iodine. I worked with helium neon plus iodine. So iodine 129, remember the 29 in a cell within the laser. Now this is something very interesting, because if you put anything, if you know about lasers, if you put anything in the laser cavity, laser stops. Do you know why? Because laser works on the principle gain is just above the loss. If gain is equal to loss or gain is less than loss, the laser beam won't work. You know the multiple transitions between two mirrors, right? So anything that I put in a laser cavity, it spoils it. And yet I'm putting iodine 127 with, of course, a cold finger so that it was not too pressurized. Otherwise, my laser would go at a low pressure, low temperature. Okay? I used 4 degrees centigrade, I think, with a Peltier cooler. Okay? Now this worked, because not only did I cool the system, therefore the Doppler curve becomes narrower, but I used a very thin single mode laser. That's a different thing how to get there, and moved it according to my electronic piezoelectric transducer, moving a mirror. By the way, I moved it by a ramp. The electronic circuit I built was a ramp. All of you know what a ramp is, right? This one. It's a triangle which goes up linear and comes down very fast. So as it goes up, it pushed a mirror. My mode traveled across the Doppler. And as it traveled across the Doppler, it did this little trick of finding these little peaks. Inverse lamp dip. Now, if you want to know a little more, it's a peak and not a lamp dip was a down. Peak is opposite of lamp dip. Just give me one minute. So the whole thing is to understand why a dip becomes a peak. Cartoon for that, which I drew even in my thesis. So suddenly that dip becomes a peak, but it becomes a peak for every little hyperfine structure. And therefore, I have got rid of the Doppler effect. Okay, this was my first part, so that then I could then lock the laser onto the peak. Otherwise, there was no way to do it. Just one second. Yeah, there it is. Don't laugh. It's a joke. But my referee laughed when he took my viva. Can you see it? It says under the Doppler line. So there's a genie sitting inside and pushes the Doppler line thick with pressure. Then what happens? Suddenly in his head there is a dip. That's the lamp dip. And then what happens? He gets a choti. That's the inverse lamp dip. You understand? So this is just a fun way of explaining under the Doppler width. I sketched this. So you push it, the FWHM becomes thicker because of pressure and temperature. Then you do a trick and you get the lamp dip, which is a very narrow dip. And then you do something else and you get an inverse lamp dip, which is a peak. If I get this peak, and remember I got 23 peaks, I could lock on my system. And that's the whole beauty of electronics and lock-in amplifier. Something which is, I wish I could, share this with you, because when I was doing it, half of Mod Lab used to come to my lab to see what is the lock-in amplifier. There were times when this was not known, but boxcar integrator, lock-in amplifier, all these signal processing tools were simply fantastic. And are used all over the world, but here they came rather slowly. So we talk of amplifier and filter and things like that in electronics, but go far ahead. For example, I use a notch filter. That's in your BSc. What is a notch filter, It's the opposite of band pass. What is band pass filter? It passes only certain frequencies on both sides, correct? Low pass, high pass, band pass. What is a band stop? That's a notch. Reverse of a band pass. So I had to build a very, very sharp notch filter. It's very easy. It's two T's. Resistance, capacitance, resistance. Two inverted T's touching each other, that is the notch filter, N-O-T-C-H. Notch means a cut. And I have the graph. I did a beautiful notch filter which trapped a certain frequency and did not let it go or interfere. So these are things you learn, self-learning and trying and doing it. So it's not just optics and lasers, it's also the whole table which I made was 800 kgs. By the way, it was in Xavier's for 10 years and then finally we threw it because nobody wanted it. That 800 kg table was from a workshop at BRC, which I brought up to my second floor there, Model Labs, and made it for complete vibration free because commercial lasers were lakhs of rupees. And I was not a BRC employee, I was a university teacher working there. So I made that whole thing. And finally, the feedback loop was so good. I mean, I hope you understand what is feedback loop, isn't it? The simple thing in biology, when your hand touches something hot, why do you pull it back? It's a feedback loop. What type of feedback do you call? Come on, physics. Positive or negative? Positive means it increases with every cycle. Negative means it decreases and otherwise stable. So all biological feedback is negative because if it was positive, your hand would remain there and it go hotter and hotter till you burnt. The fact that it told that remove the hand is reduce the heat, correct? So I did use feedback loop. In what way? I moved my laser on both sides of my peak. The more it went on one side, the error signal became bigger and phase became opposite. You understand? So the error signal in a loop corrects it and brings it back. It was beautiful to see. It would shudder and come, So the electronic signal control of such a big system, remember, there's helium neon, there's Peltier cooler, there's iodine, and everything is perfect aligned. Okay? And by the way, we search for detectors. And we didn't get them in India. I had to finally use both lock-in amplifier and detector from abroad because we made them, but the things here weren't good enough. Now, of course, they are very good. I checked NPL, National Physical Laboratory. They sent detectors, but they were not good. PZT is not good because you needed something which was deadly accurate for this. Okay? X, which I talked about, that is saturation spectroscopy and inverse lamp depth. These are something different. Willis Lamb got Nobel Prize not for lamp depth, but the hydrogen levels at ground level. Okay, so his photo is there in the MSc lab, last lab. Question?
No, sir. Thank you, sir.
Okay, welcome.
Anyone
I
else
really
from the audience?
wish that when the pandemic is over, we could physically meet in a room and discuss. It's so much more different. And now also when your videos are on, I feel so happy. During my talk, I was seeing nothing. Absolutely nothing. Not even my face because I cut off my video also. Anyway, thanks a lot. If there are questions, you can send it through Akshita or we can meet again sometime whenever convenient over a Zoom meeting like this, small group. And I could give you references because we can't teach in these groups. I mean, I can show you some things, but the whole derivation or the actual thing is difficult to do. Though I have all this, in fact, tomorrow is my photography lecture where I will do portrait lighting and so many other things. It's like a studio behind me, 3 lights, 4 lights. It's difficult. I have to start working this now. That's for SIC, advertising. Okay?
Yes, sir.
Akshita,
Are there any more questions from the audience? Okay, then I think we can. Yeah, yes.
Yes, I think we can conclude. It has been a long session. And if there are any doubts or questions for anyone, I will definitely.
Yeah. please use Akshita as one person who could then forward to me. Okay.
And thank you
so much.
for your time, sir.
Yeah. Now I can't find the leave. Leave is red symbol in center. Correct.
Yes, sir.
Here we go. Bye.
Bye, sir.
And all the
Bye, sir.
best
Thank
for
you,
the
sir.
Celeritas team.
Yeah.
Thank you so much.
Yeah.
I think others can also leave. Conclude this.
Thank you, everyone.
And I'll go sleep. I think only team members here, right?
Yes, I guess.
Yeah.
अभी added है कौन सा content बच रहा है magazine के लिए सारे हो गए